afternoon, everybody. I'm Katie Schuman. I'm a research scientist at Oak Ridge. So I'm going to be talking to you today about something completely different from my normal research. So if you've seen me present before, chances are you haven't seen anything like this. So this is work in collaboration with some research scientists at Oak Ridge and some faculty and students at the University of Tennessee and Georgia Tech. So before I get into the presentation, shameless plug, we have a demo that is the typical research that you see me present on. So if you would like an update on what's going on in our research group, please stop by our demo during the poster and demo session. Our research group, the 10 Lab, spans the University of Tennessee and Oak Ridge, as well as collaborators at a variety of other institutions, including right here at SUNY Polytech. And we do everything from applications all the way down to materials. I live up in the algorithms and applications space. I'm going to talk about some hardware today. Please don't ask me questions about the hardware. We have students and faculty I can direct you to answer questions about those, and there'll be some papers that I can point you to for the hardware details as well. But if you're interested in learning more about what we do, you can visit our website here, and please stop by the demo to hear some updates on our work. Okay, so you don't need this slide because you're the neuromorphic computing community, but this is a slide that I present when I'm talking about and introducing what neuromorphic computing systems are to people who know literally nothing about neuromorphic, to people who may not know anything about machine learning, in fact. So typically your computer science crowd, your HPC crowd, things like that. So I describe neuromorphic computing as non-von Neumann computers inspired by biological brains. They can perform certain workloads with significantly less power than traditional architectures. And we've seen this resurgence in neuromorphic systems in recent years, partially due to the rise of machine learning and deep learning applications. Now, obviously, you all know that there's greater story behind this, but this is how I talk about it when I'm presenting to a broader audience. Now, what I'm going to be doing in this talk is, again, addressing what if you're a computer scientist who knows nothing about neuromorphic systems, who knows nothing about neural networks, and you want to know what neuromorphic computers are all about. And you want to figure out, like, maybe I want to program a neuromorphic computer to do something. How am I going to do that? Well, if you're a computer scientist and you walk up to a neuromorphic computing system and you're looking at it and you don't know that it's neurons and synapses, what are the properties that you are going to recognize that this system has? We've talked about a lot of these over the course of the last couple of days. Massively parallel computation, co-located processing and memory, simple processing elements that perform specific computations, simple communication between elements, usually in the form of spikes, although I don't use that language when I'm talking to people outside the community, event-driven computation. Some systems have stochastically firing neurons for noise, and they are inherently scalable, and we've seen that for the different implementations for the system. So you're a computer scientist, you see a system with these characteristics, you might say, I can do something with this system that's not just machine learning and not just neural network computation. Maybe I can try to exploit these characteristics to do a program that would run more efficiently on this architecture than it might run on another system. So a key research question, and this is something that I dabble in and is kind of a fun side project for me, which is, can we use these properties for non-neural network and non-machine learning applications? Can we leverage these systems to do something besides just what we've been talking about for most of the conference? Now, why do we care? I'm at Oak Ridge National Lab, and we have supercomputers at Oak Ridge National Lab, and we have them across a lot of our DOE sites. And so we had Titan. We still have Titan. It's going down in June. And we've moved on to Summit, which is a little bit more of a heterogeneous architecture. Each node has 6 GPUs, whereas Titan, each node had 1 GPU. And so the question is, what's the next system that we're going to build after Summit? They're already talking about what the system is going to look like. And maybe these systems are going to continue to be more heterogeneous moving forward. We're going to continue to see other accelerators that would be included in these systems. And maybe, if I had my way, that system has a neuromorphic system as an accelerator or a coprocessor in the HPC node. Now, if I'm trying to sell that, and I am, and I hope some of you are as well, then I want to be able to tell the community, hey, you can use this to do all these cool machine learning and neural network applications, and you can do neuroscience simulations on them, but also, there are other things you can do. So if you have some existing codes, maybe you can try to port them to these systems. So what are we as a community doing in this space? Well, I wrote a survey paper tried to get a handle on the full neuromorphic computing community. I tried to be as comprehensive as possible up through January 2017. If I left you out, I apologize. But tried to be as comprehensive as possible, and I looked at, one of the things was looking at the breakdown of applications. And you can see the kind of tree map of the breakdown of different types of applications that we were looking at up until that point. And less than 1% of the applications that were done in neuromorphic systems were on a non-neural network, non-machine learning application. Now, in the last couple of years, we've actually done a little bit better, and you've seen some of that work talked about over the course of the conference. I've tried to highlight a couple of the posters for some people who are presenting on things like the network flow and solving partial differential equations through neural algorithms and Markov random walks. There's a lot of good work going on at Sandia in this space. But there's these different problems that we can map onto neuromorphic systems, and we've shown that they can perform well on them. Different graph algorithms, scientific simulations, constraint satisfaction problems like the Sudoku and the graph coloring that have been talked about several times over the course of the conference. So we've talked about these over the course of the conference. You've seen them maybe in the posters. But what I want to do is I want to walk you through how you actually map two graph problems onto a neuromorphic architecture. This is my little tutorial of it's a puzzle. How do we figure out how to make a neuromorphic system solve these problems? Because my goal is that for the rest of the conference, you're going to sit down and try to figure out how to map your own problem onto a neuromorphic system, and I want to hear about it. Okay, so because I actually want to tie it to a particular implementation to give you an idea of what it looks like, I collaborate with hardware developers, and my collaborators on this have developed this system that we're looking at in simulation, which is a memristive spiking neuromorphic system. It's leaky, integrate, and fire neurons with programmable thresholds and refractory periods. The synapses have programmable delays and weights, and some form of STDP. We have different forms of STDP that we implement. But because we can characterize the behavior of the circuits, we can get these energy estimates for the different events that these neurons and synapses would be doing. And if you want more details on this, remember that I'm not the hardware person. There are papers you can go look at to get information about how we get these energy estimates. But what we can do is we can actually look at running these different algorithms, use these energy estimates, and figure out what is this actually going to look like for real graphs running on a system that would look like this. Okay, so how do you map a problem onto a neuromorphic system? First thing you're going to do is you're going to need to convert your problem into using neurons, synapses, and spikes. So you're going to have to define how you're going to set up your network. What is your network topology going to be? What are the parameters going to be? You're going to have to figure out where and when spikes should be applied, how long to run the system to get an answer back out, where and when to read the neuromorphic properties, whether that be the changes to the graph itself due to plasticity or the spikes that are coming off the system. So I'm going to walk you through two graph problems. I'm going to go into a little bit of detail for how we map them onto the system. And those problems are single source shortest path, which Mike Davies talked about earlier this week, and neighborhood subgraph extraction. So, you ready? Here we go. Single source shortest path. First thing we need to do is we need to figure out how to map the graph onto a spiking neural network. Graphs and networks are pretty similar, so this is pretty straightforward. That's why I picked this problem, because it's easy to do in 25 minutes. So, we're going to take a graph and convert it to a network. So for every vertex in our graph, we are going to create a neuron in the network with zero threshold. This basically means if it receives any charge, it's going to fire. And a long enough refractory period to make sure it fires only once. If you can't, in your neuromorphic system, implement a long enough refractory period to do that, you can add additional structure to force the neuron to only fire once as part of the simulation, but it needs to only fire once. Every neuron in the graph. And then for every edge in the graph, we are going to create a corresponding synapse in the network with a weight of 1 or unit weight or whatever kind of smallest increment weight you can implement in your neuromorphic system, and a delay proportional to the length of the edge in G. So we're going to make sure that our synapses are long enough that they're proportional to the length of the edge in the graph, so that when we're calculating a single source shortest path implementation, the synapses lengths are comparable to the edge lengths in the graph. Then what we're going to do is we are going to stimulate our source neuron, simulate for long enough for a single spike to travel along every edge in the network, so for quite a while. And then we are going to read out the spike times and the updated graph. So we're going to read out the spike times of each neuron, which is going to give us the length of the shortest path from the source node to each destination node. And if your implementation has plasticity, the edges that have been potentiated, the edges where the weights have increased, are going to tell you what the shortest path actually is on the system. So what does this look like? Suppose we are interested in calculating the shortest path from this node to every other node in the graph. We are going to stimulate this, cause it to fire. The spikes are going to propagate along the network. Here, this is an unweighted graph where every edge has the same length. And the fire times of each of the corresponding other neurons in the graph is going to tell you the length of the shortest path to that node. And the potentiated edges along the way are the ones that where the spike traveled along that synapse caused the neuron to fire. Those are the ones that increased. Those are going to tell you what the shortest paths are. Now, you'll notice that here at this last one, there are two edges coming back off of it. That's because there are two paths of the same length. So it's going to give you every shortest path, not just one shortest path. So that's how this would work. It's a pretty straightforward mapping onto a neuromorphic system. It's naturally what the system does, and it gives you the shortest path calculations, and byproduct of the plasticity also gives you the shortest paths themselves. Okay, so now let's talk about the other problem, neighborhood subgraph extraction, and how you would embed that onto a neuromorphic system. It's a slightly different process. So in this case, we're going to take a vertex, we're going to turn it into a neuron, and we're going to take edges and turn it into synapses, but our parameters are going to be slightly different. For every neuron, it's going to be a threshold of 1, and you're going to have a refractory period of 1. For the synapses, the weights are all going to be 1, but the delays are going to be 2, and you'll see why in a second. The steps for doing this is a little bit more complicated. We're going to do a little bit more communication to and from the neuromorphic system. So first thing we're going to do is stimulate the source neuron, again, the one that we're trying to find the neighborhood for. Then we're going to stimulate for 2 time steps. Why 2? This number is 2. We want to simulate for long enough just for the neighbors for that neuron to fire. At that point, we are going to read out the spike times to determine the nodes in the subnetwork, the ones that we care about that are in the neighborhood. And then we are going to create a new graph where all of the other neurons outside that neighborhood have such a high threshold that they will never fire. Or you can set up some other parameters in your system to force every other neuron to never fire. At that point, we are going to simultaneously load that new graph onto the system, but then simultaneously fire all of the neurons in the neighborhood, simulate again for 2 time steps, just long enough to travel to its immediate neighbors, and we're going to read out the graph to get the potentiated edges, which are the edges for the subgraph that we care about. What does this look like in simulation? Again, let's pick a source neuron to stimulate in this example graph. We're going to run it just long enough to get what the neighbors are. Everything that spikes within that 2 time steps is going to tell us what the neighbors are. We're going to read out which one's spiked. We're going to update every other neuron in the graph's threshold to be so high that they can't fire no matter how many spikes they receive. We're going to load the new network onto the implementation. We're going to fire all of the neurons that are within the neighborhood subgraph. They're going to send out spikes to everybody that they're connected to, but because the thresholds are so high on all of these, none of them are going to fire. The only ones that are going to fire are the ones that are in the subgraph. That means that the edges between those are the only ones that are going to potentiate, which gives us the edges for the neighborhood subgraph. So we had fun sitting in a room figuring out, like, okay, what's the right threshold, what's the right refractory period, what's the right weight, what's the right delay to force these properties to emerge. Again, I encourage you to try to figure out mapping your own problems to these systems. It's kind of a fun side project. But we actually wanted to simulate these. So here's some runtime characteristics of the different systems. What you have to do on the CPU, how many loads, so how many communications do you have to do, which are non-trivial. As Brad mentioned yesterday, I think we need to think about more communication to and from the chip. But so we have to do a single load and a single read in shortest path, but we have to do 2 loads of a network onto the implementation for the neighborhood subgraph extraction. But we have to run the neuromorphic system for a lot longer for the shortest path, where it's a constant time running for the neighborhood subgraph extraction. So we have this particular neuromorphic implementation that we were tying these 2 implementations to, these 2 embeddings to, and we wanted to look at how they would perform in a simulation on real-world graphs. And so what do these graphs look like? There are 3 graphs from the Stanford Large Network Library. There's a road network in California, a collaboration network graph from the High Energy Physics Topic on Archive, and an Amazon co-purchasing network. And these are undirected and directed graphs, and they have varying numbers of vertices and edges. And so given those energy estimates, those embeddings that I talked about, the processes that I just walked you through, we're able to simulate what these graphs would look like on those 2 problems on that neuromorphic system and get some energy estimates for it. And this is what it looks like. So when I come back with shortest path with these energy estimates for a memristive neuromorphic system, that's pretty high. At least I'm like, that feels high coming from a computer science perspective. And so I drilled down into this to see, okay, where's all the cost coming from? And it's coming from the neurons being idle. So there was a high idle cost for each of the neurons in the neuromorphic implementation. This was not something that we had a huge impact on any of our traditional neuromorphic runs on the performance on the system for the traditional spiking neural network use cases. But now it's a problem. It's a problem for these workloads. And so I think it's important for us to be considering when we're looking at these developing new neuromorphic systems, different workloads beyond just the spiking neural network use case, because we may have issues in our hardware implementation that are only going to arise for workloads like these. Okay, what about other hardware? So we collaborate with a lot of different groups that are developing hardware. We develop a lot of hardware within our research group itself. And so a question for me is, all right, I can embed these problems onto that one spiking memristive neuromorphic implementation. Can I also embed them on these other implementations? And then what are the performance consequences on those? So these are the implementations we looked at. These two were developed at the University of Tennessee. This one is a NIST implementation that Jeff Shainline presented on. He's in that group earlier this week, an optoelectronic implementation. So Dana 2 is a fully digital implementation. We have two versions, one that's programmable and one that's application specific. Mr. Dana is another memristive implementation, but it's different from the one I talked about previously. And then, as I mentioned, SOAN is an optoelectronic implementation. And every one of these has different architectural characteristics. So they have slightly different neuron models, slightly different synapse models. The way that they're implemented on the systems are very different, and obviously the underlying devices are very different. So we looked at a smaller network for this one. This is kind of a contrived example, but it's a graph that is inspired by a city street layout where we have some one-way streets and avenues and some two-way streets and avenues, and each of the nodes represents an intersection. And here we just wanted to find the length of the shortest path and not the paths themselves, because not all of our implementations have plasticity implemented on them. So what does it look like in terms of network size? So the network sizes themselves for 3 of the implementations, you could directly map. You could use the exact same embedding process that you did previously in order to embed the graph onto the neuromorphic system. But for the optoelectronic implementation, because it has slightly different characteristics, in particular the delays are on the neurons and not on the synapses, it requires a little bit more structure to be able to realize the same implementation. But because it's optoelectronics, the energy usage is very, very small. But we can start to compare the performance, again, of these different neuromorphic implementations in terms of energy usage and how difficult it is to embed these problems by looking at an example graph like the one I showed previously. Okay, so my goal for this talk was to, one, encourage you to, in your spare time, when you get exhausted with working with your hardware or your algorithms, is to try to figure out how would I map a problem onto a neuromorphic system if I forget that it's a spiking neural network. It is non-trivial, and even for graph algorithms where the mapping is relatively natural. The other thing is that these sort of tasks can have radically different performance profiles from what we're typically looking at in neuromorphic systems, and I think it's worthwhile to look at tasks like that. Our goal here was not to show that a neuromorphic system is necessarily better at solving these graph algorithms than a GPU or a CPU at solving these tasks. The point was to show that a neuromorphic system can solve these problems. And so if your CPU and GPU and your FPGA and your quantum whatever and your future extremely heterogeneous node is super busy and you need to do shortest path calculations, your neuromorphic system can do it if you need it to. If you're interested in more of the theory and the math background on this work, we have a paper we just put up on arXiv yesterday that goes into some of the more mathematical theoretical underpinnings of what's going on here. With that, I will thank my collaborators at Oak Ridge, at the University of Tennessee, and at Georgia Tech. This is the hardware team. And shameless plug time. I'm a co-organizer of ICONS, the International Conference on Neuromorphic Systems, a sister meeting, if you will, of NICE. And I encourage you to join us at ICONS. It's in July in Knoxville. The submission deadline is currently April 15th. We are accepting short and full papers for for our proceedings. We're also accepting posters and short talk submissions, as well as submissions to do tutorials and workshops and special sessions. So if you're interested in doing any of those things, please visit our website, or you can come talk to me more about icons. I hope that you'll join us there. And with that, I'll thank you, and I'm happy to take any questions.
Thank you, Katie. You made excellent time, and you were also able to plug it for icons.
Yeah.
So good job about that.
So you told us how to do undirected graphs.
Yes.
I'm sorry, directed graphs.
You can also do undirected.
I saw that.
Yes.
How do you do that when a neural network is inherently?
You create 2 synapses for every one edge.
Okay.
Yeah, so you have, for an undirected edge, you create one in one direction and one in the other, and it's still able to do the problem. Yeah.
Thank you. Did you study the effect of parameter noise on your algorithms?
We haven't done that yet, but it is something that our hardware developers are working on, specifically for systems like the memristive-based systems where that would be an issue that would be of interest. I think what you could do for some of these problems is be able to scale the parameters in such a way that it would be less of an issue, but it's certainly something that we are interested in looking at.
Thank you.
Question.
Excuse me. I think very interesting to see this graphic method using for the neuromorphic computing. But right now, you assume each path is the same length. So you actually from 0 to 1, 1 to 2, is all count by 1. If they have a weight, or say you assume the distance is different, then the result may be different.
Right, so in the neuromorphic implementation, if you can do a delay on your synapse, you can realize weighted links. So in the example I showed, they didn't have weights, but you can do that. I think actually for this example, these edges are all weighted, so they all have a particular length. They're still able to implement that on all of our neuromorphic systems because either the synapses or the neurons have a delay that we can encode that distance into.
I guess it depends on the specific type of neuromorphic chip, but basically I think that in your energy consumption, you're assuming that the embedding is free.
That's right. So we aren't considering the embedding cost. We aren't considering the CPU cost in the energy calculations. They weren't really meant to compare like how a neuromorphic system would perform against a traditional CPU or GPU implementation. They're meant to compare each other, but you still may have different costs for the embedding for the different neuromorphic implementations. So it's worth considering.
I just mean it because in some of those algorithms, the cost is pretty much the cost of reading the graph, right? If you have like of the edges, then, well, basically.
You can solve, yeah. So yes, so you do want to consider the embedding costs and how much work you're going to actually have to do to map it to your neuromorphic system. A thing I didn't mention here is we also assumed that all of these topologies can be directly embedded onto the system, so it doesn't require any, that assumes your system doesn't have any connectivity restrictions, which may be a poor assumption, so there may be additional embedding issues there. But I think the point here was just that you can solve problems like this on a neuromorphic system, and I think it's worthwhile to keep thinking about these problems. I just wanted to kind of get y'all thinking about it. Thanks.
Thanks, Katie. Let's thank her again.